We will solve 5 questions here from our integration practice series, so it's easier for viewers to move from easier to complex questions later on. Starting with the integral of e raised to the power x plus 3, plus e power x minus 3.
Oh, that looks easy.
Rejoice, it's an easy one. I've put this question just to review some basic properties of exponentials and integrals. For this, you rewrite the function as e power x times e cubed plus e power x over e cubed. Now, due to the sum property of integrals, we can write the integration sign separately on both terms. E cubed is just a constant in both, so it can be factored out. This makes the functions inside the integral as just e power x, whose integral is the same thing. Hence, the answer is e raised to the power x plus 3, plus e power x minus 3, plus c.
The answer is the same as the question. Nice!
Next, we solve the integral of 4 over x times 1 plus 4 ln x whole squared.
Really, another rational function.
Don't blame me when the possibilities of questions are endless.
Fair enough.
All right, back to the question. It's a rational function, so we first look if it is either in the form to be integrated directly to get natural log function, or we can look to factorize it.
But since this is already factorized, we see that it is not in the form of an inverse trigonometric function, neither can we apply partial fractions here. We should use u substitution.
Exactly. Good job. For u substitution, we generally substitute the most complex term as u, or something that is inside brackets and is raised to power. In this case, we substitute u as 1 plus 4 ln x. Taking the derivative, du over dx gives 4 over x. Rearranging this, we get x du equals 4 dx. And making dx the subject, we have x over 4 du. All right, we plug this back in to get the integral of 4 over x times u squared times x over 4 du. The x and the 4's cancel out, leaving us with 1 over u squared du.
And we can write this in the numerator as u to the power negative 2.
And evaluating that gives negative u to the power negative 1 plus c, or negative 1 over u plus c. Plug back in the value of u to get negative 1 over 1 plus 4 ln x plus c.
Wow, that was simple.
If you know how to choose what technique to use, then any question is made simpler. And that is exactly what we teach you here. Let's do a rational function integral today. Integrate x squared over 1 plus x power 6. First, we check if this can be factorized, or can we use algebra on it in some way?
Seems like we can't, and so partial fractions is out of the question. However, we can use u substitution, choosing u as x cubed.
Correct! If you're just joining the series, then it might seem weird, but we have learnt how to narrow down options. And choosing u as x cubed works as we need to get rid of the term on top. And to do that, the u term needs to have a greater power than it. Du over dx gives 3x squared, and dx equals du over 3x squared. And in the denominator, we can write the x power 6 as u squared. Furthermore, the x squares cancel out, leaving us with just terms of u. Factoring out 1 over 3, the integral is du over 1 plus u squared, which is equal to arctan u. And plugging back the value for u gives the final answer, 1/3 tan inverse of x cubed plus c. Moving on to a little more difficult one. We evaluate the integral of x squared minus x power 4 whole square root.
From what I've learned from the videos so far, is that right now we cannot directly integrate this. None of our methods work. So we should start by doing some algebra.
Wow, you're spot on. First, we identify the possible methods we can use to rewrite the function.
I can identify 2 of them. We can use the difference of squares formula, or we can factor x square. But which one do I use?
Since we have a square root on top, then factorising x squared out is the option to go with. This way we have the square root of x squared times 1 minus x squared. And when two terms are being multiplied like this in a square root, we can write it as two separate terms, like that. The root of x squared is just x, hence our function is simplified to x times the square root of 1 minus x squared.
All right, we have two terms now. So can I use either u substitution or integrate by parts?
Well, since the difference in powers between the x's is 1, we will use u substitution, choosing u as equal to 1 minus x squared. Du over dx will equal negative 2x, and dx equals du over negative 2x. Plugging it back in, we have the integral of x times root u times du over negative 2x. The x's cancel out, and we can factor out the negative and constants to write this as negative 1 over 2 times the integral of root of u du. Then we evaluate the integral using power rule. So negative 1 over 2 comes as is, times 2 over 3 times u power 3 over 2 plus c. The 2's cancel out, giving us negative 1 over 3 times u power 3 over 2 plus c. Plugging back in the value of u gives us the final answer, negative 1 minus x squared in brackets, whole power 3 over 2 divided by 3 plus c. For the final question, we will be solving the tricky integral e raised to the whole power x plus e power x times dx. First of all, using the exponent product law, we write this as the integral of e power x times e to the e power x, thereby writing this as two terms. Now we have two options, u substitution or integration by parts. We clearly cannot use integration by parts here, as the equation won't simplify no matter which u or dv values we choose. So we use u substitution and choose u equal to e power x. This way, the greatest number of terms are simplified and seems like the obvious first choice. If it does not work, we can try other substitutions. So du over dx equals e to the x, and dx equals du over e to the power x. Since u equals e to the power x, we can write this as du over u, then substituting back into the main question. It becomes the integral of u times e power u times du over u. The two u's cancel out, and we are left with the integral of e power u du, which is just e power u plus c. Substituting back in the value of u, we get the final answer, e raised to the power e power x plus c.